In this video, I'm going to talk about improving generalization by reducing the overfitting that occurs when a network has too much capacity for the amount of data it's given during training. I'll describe various ways of controlling the capacity of a network, and I'll also describe how we determine how to set the metaparameters when we use a method for controlling capacity. I'll then go on to give an example where we control capacity by stopping the learning early. Just to remind you, the reason we get overfitting is because, as well as having information about the true regularities in the mapping from the input to output, any finite set of training data also contains sampling error. There's accidental regularities in the training set just because of the particular training cases that were chosen. So when we fit the model, it can't tell which of the regularities are real and would also exist if we sampled the training set again, and which are caused by the sampling error. So the model fits both kinds of regularity, and if the model's too flexible, it'll fit the sampling error really well, and then it'll generalize badly. So we need a way to prevent this overfitting. The first method I'll describe is by far the best, and it's simply to get more data. There's no point coming up with fancy schemes to prevent overfitting if you can get yourself more data. Data has exactly the right characteristics to prevent overfitting. The more of it you have, the better, assuming your computer's fast enough to use it. A second method is to try and judiciously limit the capacity of the model so that it's got enough capacity to fit the true regularities, but not enough capacity to fit the spurious regularities caused by the sampling error. This, of course, is very difficult to do, and I'll describe in the rest of this lecture various approaches to trying to regulate the capacity appropriately. In the next lecture, I'll talk about averaging together many different models. If we average models that have different forms and make different mistakes, the average will do better than the individual models. We could make the models different just by training them on different subsets of the training data. This is a technique called bagging. There's also other ways to mess with the training data to make the models as different as possible. And the fourth approach, which is the Bayesian approach, is to use a single neural network architecture, but to find many different sets of weights that do a good job of predicting the output. And then on test data, you average the predictions made by all those different weight vectors. So there's many ways to control the capacity of a model. The most obvious is via the architecture. You limit the number of hidden layers and the number of units per layer, and this controls the number of connections in the network, i.e. the number of parameters. A second method, which is often very convenient, is to start with small weights and then stop the learning before it has time to overfit, again on the assumption that it finds the true regularities before it finds the spurious regularities that are just to do with the particular training set we have. I'll describe that method at the end of this video. A very common way to control the capacity of a neural network is to give it a number of hidden layers, or units per layer, that's a little too large, but then to penalize the weights using penalties or constraints on the squared values of the weights or the absolute values of the weights. And finally, we can control the capacity of a model by adding noise to the weights or by adding noise to the activities. Typically, we use a combination of several of these different capacity control methods. Now, for most of these methods, there's metaparameters that you have to set, like the number of hidden units, or the number of layers, or the size of the weight penalty. An obvious way to try and set those metaparameters is to try lots of different values of one of the metaparameters, like, for example, the number of hidden units, and see which gives the best performance on the test set. But there's something deeply wrong with that. It gives a false impression of how well the method will work if you give it another test set. So the settings that work best for one particular test set are unlikely to work as well on a new test set that's drawn from the same distribution, because they've been tuned to that particular test set. And that means you get a false impression of how well you would do on a new test set. Let me give you an extreme example of that. Suppose the test set really is random. Quite a lot of financial data seems to be like that. So the answers just don't depend on the inputs, or can't be predicted from the inputs. If you choose the model that does best on your test set, that will obviously do better than chance, because you selected it to do better than chance. But if you take that model and try it on new data that's also random, you can't expect it to do better than chance. So by selecting a model, you get a false impression of how well a model will do on new data. And the question is there a way around that? So here's a better way to choose the metaparameters. You start by dividing the total data set into 3 subsets. You have the training data, which is what you're going to use to train your model. You hold back some validation data, which isn't going to be used for training, but is going to be used for deciding how to set the metaparameters. In other words, you're going to look at how well the model does on the validation data to decide what's an appropriate number of hidden units, or an appropriate size of weight penalty. But then once you've done that, and trained your model with what looks like the best number of hidden units and the best weight penalty, you're then going to see how well it does on the final set of data that you've held back, which is the test data. And you must only use that once. And that'll give you an unbiased estimate of how well the network works. And in general, that estimate will be a little worse than on the validation data. Nowadays in competitions, the people organising the competitions have learned to hold back that true test data and get people to send in predictions so they can see whether they really can predict on true test data or whether they're just overfitting to the validation data by selecting metaparameters that do particularly well on the validation data but won't generalize to new test sets. One way we can get a better estimate of our weight penalties or number of hidden units or anything else we're trying to fix using the validation data is to rotate the validation set. So we hold back a final test set to get our final unbiased estimate, but then we divide the other data into n equal size subsets, and we train on all but one of those n and use the nth as a validation set. Then we can rotate and hold back a different subset as a validation set, and so we can get many different estimates of what the best weight penalty is or the best number of hidden units is. This is called n-fold cross-validation. It's important to remember the n different estimates we get are not independent of one another. If, for example, we were really unlucky and all the examples of one class fell into one of those subsets, we'd expect to generalize very badly. And we'd expect to generalize very badly whether that subset was the validation set or whether it was in the training data. So now I'm going to describe one particularly easy to use method for preventing overfitting. It's good when you have a big model and a small computer, and you don't have the time to train a model many different times with different numbers of hidden units or different sized weight penalties. What you do is you start with small weights, and as the model trains, they grow, and you watch the performance on the validation set, and as soon as it starts to get worse, you stop training. Now, the performance on the validation set may fluctuate, particularly if you're measuring an error rate rather than a squared error or a cross-entropy error, and so it's hard to decide when to stop. And so what you typically do is keep going until you're sure things are getting worse, and then go back to the point at which things were best. The reason this controls the capacity of the model is because models with small weights generally don't have as much capacity, and the weights haven't had time to grow big. It's interesting to ask why small weights lower the capacity. So consider a model with some input units, some hidden units, and some output units. When the weights are very small, if the hidden units are logistic units, their total inputs will be close to 0, and they'll be in the middle of their linear range. That is, they'll behave very like linear units. What that means is, when the weights are small, the whole network is the same as a linear network that maps the inputs straight to the outputs. So if you multiply that weight matrix W1 by the weight matrix W2, you'll get a weight matrix that you can use to connect the inputs to the outputs. And provided the weights are small, a net with a layer of logistic hidden units will behave pretty much the same as that linear net, provided we also divide the weights in the linear net by 4 to take into account the fact that when there's hidden units there, in their linear region they have a slope of 1/4. So it's got no more capacity than the linear net. So even though in that network I'm showing you there's 3 times 6 plus 6 times 2 weights, it's really got no more capacity than a network with 3 times 2 weights. But as the weights grow, we start using the non-linear region of the sigmoids, and then we start making use of all those parameters. So if the network has 6 weights at the beginning of learning and has 30 weights at the end of learning, then we could think of the capacity as changing smoothly from 6 parameters to 30 parameters as the weights get bigger. And what's happening in early stopping is we're stopping the learning when it has the right number of parameters to do as well as possible on the validation data. That is, when it's optimized the trade-off between fitting the true regularities in the data and fitting the spurious regularities that are just there because of the particular training examples we chose. In this video, I'll talk about how we can control capacity by limiting the size of the weights. The standard way to do this is to introduce a penalty that prevents the weights from getting too large, with the implicit assumption that a network with small weights is somehow simpler than a network with large weights. There are several different penalty terms we can use, and it's also possible to constrain the weights so that the incoming weight vector to each of the hidden units is not allowed to be longer than a certain length. The standard way to limit the size of the weights is to use an L2 weight penalty, which means that we penalize the squared value of the weight. This is sometimes called weight decay in the neural network literature, because the derivative of that penalty acts like a force pulling the weight towards 0. This weight penalty keeps the weights small unless they have big error derivatives to counteract it. So if you look at what the penalty term looks like, as the weight moves away from 0, you get this parabolic cost. If you look at the equation, the cost that you're optimizing is the normal error that you're trying to reduce, plus a term which is the sum of the squares of the weights with a coefficient in front, lambda, and we divide by 2 so that when we differentiate the 2's cancel. That coefficient in front of the sum squared weights is sometimes called the weight cost. That determines how strong the penalty is. If you differentiate, you can see the derivative of this cost is just the derivative of the error plus something that's to do with the size of the weight and the value of lambda. That derivative will be 0 when the magnitude of the weight is 1 over lambda times the magnitude of the derivative. So the only way you can have big weights when you're at a minimum of the cost function is if they also have big error derivatives. And this makes the weights much easier to interpret. You don't have a whole lot of weights that are large but aren't doing anything. The effect of an L2 penalty on the weights is to prevent the network from using weights that it doesn't need. This often improves generalization a lot because it can use those weights that it doesn't really need to fit the sampling error. It also makes a smoother model in which the output changes more slowly as the input changes. So if the network has 2 very similar inputs, when you put in an L2 weight penalty, it prefers to put half the weight on each of those 2 similar inputs rather than all of the weight on one, as shown on the right here. If the 2 inputs are very similar, those 2 networks will produce very similar outputs, but the one with the halved weights will have much less extreme changes in its output when you change the inputs. There are other kinds of weight penalty. For example, an L1 penalty, where the cost function is just this V shape. So here what we're doing is we're penalising the absolute values of the weights. This has the nice effect that it drives many of the weights to be exactly zero, and that helps a lot in interpretation. If there's only a few non-zero weights left, it's much easier to understand what's going on. We can also use weight penalties that are more extreme than L1, where the gradient of the cost function actually gets smaller when the weight gets really big. This allows the network to keep large weights without them being pulled towards zero. It's just the small weights that will get pulled towards zero. So we then are even more likely to get nets with a few large weights. Instead of putting penalties on the weights, we could actually use weight constraints. What I mean by that is instead of penalising the squared value of each weight separately, we put a constraint on the maximum squared length of the incoming weight vector of each hidden unit or output unit. When we update the weights, if the length of that incoming vector gets longer than allowed by the constraint, we simply scale the vector down by dividing all the weights by the same amount until its length fits the allowed length. Using weight constraints like this has a number of advantages over weight penalties, and I found they work noticeably better. It's much easier to select a sensible value for the squared length of the incoming weight vector than it is to select a weight penalty. That's because logistic units have a natural scale to them, so we know what a weight of 1 means. Using weight constraints also prevents hidden units getting stuck near zero with all their weights being tiny and not doing anything useful, because when all their weights are tiny, there's no constraint on the weights, so there's nothing preventing them growing. Weight constraints also prevent the weights from exploding. One other subtle thing that weight constraints do is that when a unit hits its constraint, the effective penalty on all of its weights is determined by the big gradients. So if some of the incoming weights have very big gradients, they'll be trying to push the length of the incoming weight vector up, and that will push down on all the other weights. So in effect, if you think of it like a penalty, the penalty scales itself so as to be appropriate for the big weights and to suppress the small weights. This is much more effective than a fixed penalty at pushing irrelevant weights towards zero. For those of you who know about Lagrange multipliers, the penalties are then just the Lagrange multipliers required to keep the constraint satisfied. In this video, I'll talk about another way of restricting the capacity of a neural network. We can do that by adding noise either to the weights or to the activities. I'll start by showing that if we add noise to the inputs in a simple linear network that's trying to minimize a squared error, that's exactly equivalent to imposing an L2 penalty on the weights of the network. I'll then describe uses of noisy weights in more complicated networks, and I'll finish by describing a recent discovery that extreme noise in the activities can also be a very good regularizer. So let's look at what happens if we add Gaussian noise to the inputs to a simple neural network. The variance of the noise gets amplified by the squared weights on the connections going into the next hidden layer. If we have a very simple net with just a linear output unit that's directly connected to the inputs, the amplified noise then gets added to the output. So if you look at the diagram, we put in an input xi with additional Gaussian noise that's sampled from a Gaussian with zero mean and variance sigma I squared. That additional noise has its variance multiplied by the squared weight. It then goes through the linear output unit j, and so what comes out of j is the yj that would have come out before, plus Gaussian noise that has zero mean and has variance wi squared sigma I squared. This additional variance makes an additive contribution to the squared error. You can think of it like Pythagoras' theorem, that the squared error is going to be the sum of the squared error caused by yj and this additional noise, because the noise is independent of yj. So when we minimize the total squared error, we'll minimize the squared error that would come out if it was a noise-free system, and in addition we'll be minimizing that second term. That is, we'll be minimizing the expected squared value of that second term, and the expected squared value is just wi squared sigma I squared, so that corresponds to an L2 penalty on wi with a penalty strength of sigma I squared. For those of you who like math, I'm going to derive that on this slide. If you don't like math, you can just skip this slide. The output, y noisy, when we add noise to all of the inputs, is just what the output would have been with a noise-free system, the sum over all the inputs of wi xi, plus wi times the noise that we added to each input. And those noises are sampled from a Gaussian with zero mean and variance sigma I squared. So if we compute the expected squared difference between y noisy and the target value t, that's the quantity that's shown on the left-hand side of the equation, and I'm using an e followed by square brackets to mean an expectation. That's not the error, that's an expectation. And what we're computing the expectation of is the thing in the square brackets. So in this case, we're computing the expectation of the squared error that we'll get with the noisy system. So if we substitute the equation above for y noisy, we need the expectation of y plus the sum over all the I of wi epsilon I So when we complete the square, the first term we get is y minus t squared, and that's not inside an expectation bracket because it doesn't involve any noise. The second term is the cross product of the two terms above, and the third term is the square of the last term. Now that equation simplifies a lot. In fact, it simplifies down to the normal squared error plus the expectation of wi squared epsilon I squared summed over all I. The reason it simplifies is because epsilon I is independent of epsilon j. So if you look at the last term, when we multiply out that square, all of the cross terms have an expected value of 0, because we're multiplying together two independent things that are zero mean. If you look at the middle term, that also has an expectation of 0, because each of the epsilon i's is independent of the residual error. So we can rewrite the expectation of the sum over all I of wi squared epsilon I squared as simply the sum over all I of wi squared sigma I squared, because the expectation of epsilon I squared is just sigma I squared, because that's how we generated epsilon I. And so we see that the expected squared error we get is just the squared error we get in the noise-free system plus this additional term, and that looks just like an L2 penalty on the wi, with the sigma I squared being the strength of the penalty. In more complex nets, we can restrict the capacity by adding Gaussian noise to the weights. This isn't exactly equivalent to an L2 penalty, but it seems actually to work better, especially in recurrent networks. So Alex Graves recently took his recurrent net that recognizes handwriting and tried it with noise added to the weights, and it actually works better. We can also use noise in the activities as a regularizer. So suppose we use backpropagation to train a multi-layer neural net with logistic hidden units. What's going to happen if we make the units binary and stochastic on the forward pass, but then we do the backward pass as if we'd done the normal deterministic forward pass using the real values? So we're going to treat a logistic unit in the forward pass as if it's a stochastic binary neuron. That is, we compute the output of the logistic, p, and then we treat that p as the probability of outputting a 1. And in the forward pass you make a random decision whether to output a 1 or a 0 using that probability. But in the backward pass, you use the real value of p for back-propagating derivatives through the hidden unit. This isn't exactly correct, but it's close to being a correct thing to do for the stochastic system if all of the units make small contributions to each unit in the layer above. When we do this, the performance on the training set is worse, and training is considerably slower. It may be several times slower. But it does significantly better on the test set. This is currently an unpublished result. In this video, I'm going to describe the Bayesian approach to fitting models using a simple coin tossing example. If you already know about the Bayesian approach, you can skip this video. The main idea behind the Bayesian approach is that instead of looking for the most likely setting of the parameters of a model, we should consider all possible settings of the parameters and try and figure out for each of those possible settings how probable it is given the data we observed. The Bayesian framework assumes that we always have a prior distribution for everything. That is, for any event you might care to mention, I have to have some prior probability that that event might happen. The prior might be very vague. So what's happening is, our data gives us a likelihood term, we combine it with our prior, and then we get a posterior. The likelihood term favours settings of our parameters that make the data more likely. It can disagree with the prior, and in the limit, if we get enough data, however unlikely the prior is, the data can overwhelm it, and in the end, with enough data, the truth will out. That is, even if your prior is wrong, you'll end up with the right hypothesis. But that might take an awful lot of data if you thought things were very unlikely under your prior. So let's start with a coin tossing example. Suppose you don't know anything about coins, except that they can be tossed, and when you toss a coin, you get either a head or a tail. And we're also going to assume you know that each time you do that, it's an independent decision. So our model of a coin is going to have one parameter p. This parameter p determines the probability that the coin will produce a head. What happens now if we see 100 tosses and there are 53 heads? What is a good value for p? Well, obviously you're tempted to say 0.53, but what's the justification for that? The frequentist answer, which is also called maximum likelihood, is to pick the value of p that makes the observations most probable, and that value of p is 0.53. It's not obvious that's true. Let's derive that. So the probability of a particular sequence that contains 53 heads and 47 tails could be written out by writing down p every time you toss a head and 1 minus p every time you toss a tail. And then if we collect all the p's together and all the 1 minus p's together, we get p to the 53 and 1 minus p to the 47. If we now ask, how does the probability of observing that data depend on p? We can differentiate with respect to p, and we get the expression shown here. And if we then set that derivative to 0, we discover that the probability of the data is maximized by setting p to be 0.53. So that's maximum likelihood. But there's some problems with using maximum likelihood to decide on the parameters of a model. Suppose, for example, we only tossed the coin once and we got one head. It doesn't really make sense to say we think the probability of the coin coming down heads in future is 1. That would mean we'd be willing to bet at infinite odds that it can't come down tails, and that seems ridiculous. It's sort of intuitively obvious that a much better answer is 0.5, but how can we justify that? More importantly, we can ask, is it reasonable to give a single answer? We don't know much, we don't have much data, and so we're unsure about what the value of p is. So what we really ought to do is refuse to give a single answer and instead give a whole probability distribution across possible answers. An answer like 0.5 is fairly likely. An answer like 1 is maybe still pretty unlikely if we have some prior belief that coins come down heads half the time. So now I'm going to go through an example where we start with some prior distribution over parameter values, and we'll pick a prior distribution that's easy to work with, not one that necessarily fits what we really believe about coins. And then we'll show how that prior distribution gets modified by data if we adopt the Bayesian approach. So we're going to start with a prior distribution that says all the different values of p are equally likely. We believe that coins come biased to various extents, and any amount of bias is equally likely, so that some coins come down heads half the time, other coins come down heads all the time, and those two kinds of coins are equally likely. We now observe a coin coming down heads. So what we do now is for each possible value of p, we take its prior probability, and we multiply by the probability that we would have observed a head given that that value of p is the correct one. So for example, if we take the value of p equal to 1, which says coins come down heads every time, then the probability of observing a head would be 1. There would be no alternative. And if we take the value of p to be 0, the probability of observing a head would be 0. And if we take it to be 0.5, the probability of observing a head would be 0.5. So we take that red line, that's our prior, and we multiply each point on that by the probability of observing a head according to that hypothesis, and now we get the sloping line. That's our unnormalized posterior. It's unnormalized because the area under that line doesn't add up to 1. And of course, for a probability distribution, the probabilities of all the alternative events have to add to 1. So the last thing we do is we renormalize it. We scale everything up so the area under the curve is 1. And now if we started with a uniform prior distribution over p, we end up with this triangular posterior distribution over p, having observed one head. Now let's do it again, and this time let's suppose we get a tail. So the prior distribution we start with now is the posterior distribution we had after observing our one head, and now the green line shows the probability that we will get a tail according to each of those hypotheses that correspond to a value of p. So for example, if p is 1, the probability we would observe a tail is 0. So we have to multiply our prior by our likelihood term, and now we get a curve like that. Then we have to renormalize to make the area be 1, and that's now our posterior distribution after having observed one head and one tail. And notice it's a pretty sensible distribution. After observing one of each, we know that p can't be either 0 or 1, and it also seems very sensible that the most likely thing is now in the middle. If we do this again another 98 times, and keep applying the same strategy of multiplying the posterior we had after the last toss by the likelihood of observing that event given the various different settings of the parameter p, and let's suppose we get 53 heads and 47 tails in all, then we'll end up with a curve that looks like this. It'll have its mean at 0.53 because we started with a uniform prior, and it'll be fairly sharply peaked about 0.53, but it'll allow other values, like 0.49 is a perfectly reasonable value under this curve. Not quite as likely as 0.53, but very reasonable, whereas a value like 0.25 is extremely unlikely under this curve. So we can summarize all that with Bayes' theorem. The term in the middle of this equation is the joint probability of a set of parameters, W, and some data, D. And for supervised learning, the data is going to consist of the target values. So we assume that we're given the inputs, and the data consists of the target values that are associated with those inputs. That's what we observe. That joint probability can be rewritten as the product of an individual probability and a conditional probability. So on the right we've written it as P of W times P of D given W. And on the left I've written it as P of D times P of W given D. Now we can divide both sides by P of D. And that gives us Bayes' theorem in its usual form. Bayes' theorem says that the posterior probability of a particular value of W, given the data D, is just the prior probability of that particular value of W times the probability, given that particular value of W, that you would have observed the data you observed. And that has to be normalized by P of D, the probability of the data, which is simply the integral over all possible values of W of P of W, P of D given W. The bottom line needs to be the sum of the top line over all possible values of W in order for this to be a probability distribution that adds to 1. Because that P of D has integrated over all possible values of W, it's not affected by picking a particular value of W on the left-hand side. So when we're looking for the best value of W, for example, we can ignore P of D. It doesn't depend on W. The other two terms on the right-hand side, however, do depend on W. In this video, I'm going to talk about the Bayesian interpretation of weight penalties. In the full Bayesian approach, we try to compute the posterior probability of every possible setting of the parameters of a model. But there's a much reduced form of the Bayesian approach, where we simply say, I'm going to look for the single set of parameters that is the best compromise between fitting my prior beliefs about what the parameters should be like and fitting the data I've observed. This is called maximum a posteriori learning, and it gives us a nice explanation of what's really going on when we use weight decay to control the capacity of a model. I'm now going to talk a bit about what's really going on when we minimize a squared error during supervised maximum likelihood learning. Finding the weight vector that minimizes the squared residuals, that is, the differences between the target value and the value predicted by the net, is equivalent to finding a weight vector that maximizes the log probability density of the correct answer. In order to see this equivalence, we have to assume that the correct answer is produced by adding Gaussian noise to the output of the neural net. So the idea is we make a prediction by first running the neural net on the input to get the output, and then adding some Gaussian noise, and then we ask, what's the probability that when we do that, we get the correct answer? So the model's output is the center of a Gaussian, and what we're interested in is having the target value have high probability under that Gaussian, because the probability of producing the value t, given that the network gives an output of y, is just the probability density of t under a Gaussian centered at y. So the math looks like this. Let's suppose that the output of the neural net on training case C is yc, and this output is produced by applying the weights W to the input C. The probability that we'll get the correct target value when we add Gaussian noise to that output yc is given by a Gaussian centered on yc. So we're interested in the probability density of the target value under a Gaussian centered at the output of the neural net. And on the right here, we have that Gaussian distribution with mean yc. We also have to assume some variance, and that variance will be important later. If we now take logs and put in a minus sign, we see that the negative log probability density of the target value tc, given that the network outputs yc, is a constant that comes from the normalizing term of the Gaussian, plus the log of that exponential, with a minus sign in, which is just tc minus yc squared divided by twice the variance of the Gaussian. And so what you see is that if our cost function is the negative log probability of getting the right answer, that turns into minimizing a squared distance. It's helpful to know that whenever you see a squared error being minimized, you can make a probabilistic interpretation of what's going on, and in that probabilistic interpretation, you'll be maximizing the log probability under a Gaussian. So the proper Bayesian approach is to find the full posterior distribution over all possible weight vectors. If there's more than a handful of weights, that's hopelessly difficult when you have a nonlinear net. Bayesians have a lot of ways of approximating this distribution, often using Monte Carlo methods. But for the time being, let's try and do something simpler. Let's just try to find the most probable weight vector. So the single setting of the weights that's most probable, given the prior knowledge we have, and given the data. So what we're going to try and do is find an optimal value of W by starting with some random weight vector, and then adjusting it in the direction that improves the probability of that weight vector given the data. It'll only be a local optimum. Now, it's going to be easier to work in the log domain than in the probability domain. So if we want to minimize a cost, we'd better use negative log probs. Just an aside about why we maximize sums of log probabilities, or minimize sums of negative log probs. What we really want to do is maximize the probability of the data, which is maximizing the product of the probabilities of producing all the target values that we observed on all the different training cases. If we assume that the output errors on different cases are independent, we can write that down as the product over all the training cases of the probability of producing the target value, TC, given the weights. That is, the product of the probability of producing TC given the output that we're going to get from our network if we give it input C and it has weights W. The log function's monotonic, and so it can't change where the maxima are. So instead of maximizing a product of probabilities, we can maximize a sum of log probabilities. And that typically works much better on a computer. It's much more stable. So we maximize the log probability of the data given the weights, which is simply maximizing the sum over all the training cases of the log probability of the output for that training case given the input and given the weights. In maximum a posteriori learning, we're trying to find the set of weights that optimizes the trade-off between fitting our prior and fitting the data. So that's Bayes' theorem. If we take negative logs to get a cost, we get that the negative log of the probability of the weights given the data is the negative log of the prior term and the negative log of the data term and an extra term. So that last extra term is an integral over all possible weight vectors, and so that doesn't affect W, so we can ignore it when we're optimizing W. The term that depends on the data is the negative log probability of the target values given W, and that's our normal error term. And then the term that only depends on W is the negative log probability of W under its prior. Maximizing the log probability of a weight is related to minimizing a squared distance, in just the same way as maximizing the log probability of producing the correct target value is related to minimizing a squared distance. So minimizing the squared weights is equivalent to maximizing the log probability of the weights under a zero mean Gaussian prior. So here's a Gaussian. It's got a mean at 0, and we want to maximize the probability of the weights, or the log probability of the weights. And to do that, we obviously want W to be close to the mean 0. The equation for the Gaussian is just like this, where the mean is 0, so we don't have to put it in. And the log probability of W is then the squared weights scaled by twice the variance, plus a constant that comes from the normalizing term of the Gaussian, and isn't affected when we change W. So finally we can get to the Bayesian interpretation of weight decay, or weight penalties. We're trying to minimize the negative log probability of the weights given the data, and that involves minimizing a term that depends on both the data and the weights, namely how well we fit the targets, and a term that depends only on the weights. Is derived from the log probability of the data given the weights, which if we assume Gaussian noise is added to the output of the model to make the prediction, then that log probability is the squared distance between the output of the net and the target value, scaled by twice the variance of that Gaussian noise. Similarly, if we assume we have a Gaussian prior for the weights, the log probability of a weight under the prior is the squared value of that weight, scaled by twice the variance of the Gaussian prior. So now let's take that equation and multiply through by 2 sigma squared d. So we get a new cost function, and the first term, when we multiply through, turns into simply the sum over all the training cases of the squared difference between the output of the net and the target. That's the squared error that we typically minimize in a neural net. The second term now becomes the ratio of two variances times the sum of the squares of the weights. And so what you see is the ratio of those two variances is exactly the weight penalty. So we initially thought of weight penalties as just a number you make up to try and make things work better, where you fix the value of the weight penalty by using a validation set. But now we see that if we make this Gaussian interpretation, where we have a Gaussian prior and we have a Gaussian model of the relation of the output of the net to the target, then the weight penalty is determined by the variances of those Gaussians. It's just the ratio of those variances. It's not an arbitrary thing at all within this framework. In this video, I'm going to describe a method developed by David MacKay in the 1990s for determining the weight penalties to use in a neural network without using a validation set. It's based on the idea that we can interpret weight penalties as doing map estimation so that the magnitude of the weight penalty is related to the tightness of the prior distribution over the weights. MacKay showed that we can empirically fit both the weight penalties and the assumed noise in the output of the neural net to get a method for fitting weight penalties that does not require a validation set and therefore allows us to have different weight penalties for different subsets of the connections in a network, something that would be very expensive to do using validation sets. MacKay went on to win competitions using this kind of method. I'm now going to describe a simple and practical method developed by David MacKay for making use of the fact that we can interpret weight penalties as the ratio of two variances. After we've learned a model to minimize squared error, we can find the best value for the output variance, and the best value is found by simply using the variance of the residual errors. We can also estimate the variance in the Gaussian prior for the weights. We have to start with some guess about what this variance should be, then we do some learning, and then we use a very dirty trick called Empirical Bayes. We set the variance of our prior to be the variance of the weights that the model learned, because that's the variance that will make those weights most likely. This really violates a lot of the presuppositions of the Bayesian approach. We're using the data to decide what our prior beliefs are. So once we've learned the weights, we fit a zero mean Gaussian to the one-dimensional distribution of the learned weights, and then we take the variance of that Gaussian and we use that for our prior. Now one nice thing about that is, if there are different subsets of weights, like in different layers for example, we could learn different variances for the different layers. We don't need a validation set, So we can use all of the non-test data for training. And because we don't need validation sets to determine the weight penalties in different layers, we can actually have many different weight penalties. This would be very hard to do with validation sets. So here's MacKay's method. You start by guessing the noise variance and the weight prior variance. Actually, all you have to really do is guess their ratio. Then you do some gradient descent learning, trying to improve the weights. Then you reset the noise variance to be the variance of the residual errors, and you reset the weight prior variance to be the variance of the distribution of the actual learned weights. And then you go back round this loop again. So this actually works quite well in practice, and MacKay won several competitions this way.